Okay, this is page 4 of the Algebra 2 notes for section 6.2. And we're going to look at a concept, an easy one, called multiplicity. The idea here is that if a zero shows up multiple times, you call the number of times that it shows up its multiplicity. So what we have in this first example here is a problem that if we're written out would look like this: 3x plus 4 times 3x plus 4 times 3x plus 4 times x minus 5 times another x minus 5. Now, we don't usually write it out this way, but it's going to help me explain it. Now, the first three, all of them yield the answer of -4/3. -4/3 would zero out that one, and that one, and that one. And down here, x equals 5 is what would zero out both of these. Now, the first one shows up once, twice, 3 times. So its multiplicity is 3, whereas here it would only show up twice, so it has a multiplicity of 2. So you can put the multiplicity here. If you just do an M with a period, I'll take it to mean multiplicity. And down here, the multiplicity is 2. Now, if you're astute, you'll realize that this 3 comes from the fact that we multiply this 3 times, and that lines up with the exponent. So in the end, the exponent gives away the show here. If the multiplicity is 2, then you're going to have an exponent here of 2. All right, so those multiplicities become important in future math classes. Find the zeros and their multiplicities. So we're going to have to factor this one. It's given to us in standard form. So I'm going to first pull out the common factor, which is x to the third. And that gives x squared minus 8x plus 16. And what we have down on the end there is a perfect square trinomial. X minus 4 times x minus 4. And you'll see that I took the square root of this one and those two slots, the square root of this one and those two slots, and I borrowed the middle term there. So if I write this out, it's going to be x to the third times x minus 4 squared. Now, when you set this equal to 0, it gives x equals 0 with a multiplicity of 3. And this one, when you set it equal 0, gives x equals 4 with a multiplicity of 2. All right, so just the number of times it shows up, that's a multiplicity. Okay, there's some statements that are made often in math that are just different ways. They're synonymous with each other, and the first 4 here are actually synonyms of each other. So the factored version of this next problem is over there. And you can see that -2 and +7 would both be the zeros here. In other words, if you plugged in -2, it would zero that out. If you plug in +7, it would zero out the back half. So we're just going to concentrate on one of them, the -2. So if you look at this, you would say that -2 is a solution to the equation where you set this equal to 0. In other words, it would make a 0 in the y, and that would look like that. So that's one thing you can say, is that it's a solution to that equation. If you graph the function, you would get -2 as an x-intercept. And if you plug in -2, it would zero at the y, so we nickname it as 0. -2 is a 0 of the function, and another name for it is a root. So all of those are synonymous. Now there's a related one that's not synonymous. You would say that x plus 2 is a factor of that, and you can see that up here. X plus 2 is the factor. Foiling this out would give x squared minus 7x plus 2x would add up to that, and the back would be -14. So x plus 2 is a factor of the expression. All right, so down here is another one where we're going to maximize something, and we'll need our graphing calculator. Okay, what we have is a cardboard that starts out 16 by 12. So This length is going to be 16 inches. And this length from top to bottom here is 12 inches. And we're going to cut out these little gray corners and throw them away. When you do that, the white kind of cross-shaped center section gets folded on these fold lines here and folded up into the box shape you see on the right over here. Now, if you did that, you wouldn't have a top. This has a bottom, and I'll kind of highlight the bottom so you can see it. And if you folded all four of those flaps up, you'd get this open topped box. Okay, so what we're going to do is find out the amount to cut out of the corners. Now, what you do know about the corners is that they're squares, so it's x by x. And then this section here to here is the full length minus an x off each end. So that'll be 16 minus 2x. And a similar argument works in the vertical direction. So if the whole height of this cardboard is 12 and you take off x off that end and another x off that end, you now have 12 with 2 x's taken off. Now once you fold that box up, then this edge will be 16 minus 2x. This edge here that's not very visible is 12 minus 2x. And since we folded the flaps up, the height is x. And we're going to take that information and turn it into volume, which is length times width times height. So length times width times height. Okay, so I'm going to rearrange it by putting the x in front. And I'll keep that x in front, but I'm going to go ahead and FOIL this out. 12 times 16, let's see how much that is. I think it's 192. Outside here is minus, let me draw it more carefully, minus 32x. The inside is minus 24x. And the last times last is positive 4x squared. So I'll rearrange a little bit here. I'm going to put the 4x squared at the front where it belongs. I'll combine those two to negative 56x. And finally I'll put the 192 in the constant position at the back. So now you have to multiply by x. And we're ready to maximize the volume of this box. So go to your y equals key. Type in 4x cubed minus 56x squared plus 192. You know what? I need an x down there. Glad I caught that. 192x. Now hit zoom 6 and you're not going to see anything. Our window is not big enough to see anything. Well, I take that back. There's some kind of goofy looking lines that shoot through the problem. All right, so what's happening here is that we got a graph that's way taller than the 10 we currently have at the top of the screen. And to see that, I want you to go second table settings and make sure your graph is in, or your table is in automatic mode. Then go to your table and scroll down until you see the biggest y value. I think it's 192. All right, which tells you this graph goes really high up. So now get your window and increase the y maximum to, well, something bigger than 192. Let's go 250. And touch graph. And what you get is a graph that looks something like this. Okay, anything below the x-axis gets ignored. That part is a volume that's negative, and you can't have a volume that's negative. And if you touch the trace key and the right arrow and move until you're in this position here, you'll see that that happens when you get over there. Oh, basically anything to the right of 8. Okay? And the problem with that is if you put an 8 here and an 8 here for the x, that would be 16. 8 and 8 is 16, and this thing is only 12 to begin with, so that's impossible also. So in the end, all we care about is finding the maximum volume on that camel hump again. So go second and calc, which is above the trace key. Choose option 4 for maximum, and then move your cursor till it's basically on the left side of the hill. So you got to probably move to the left if you've been following along with me. And once your cursor is somewhere on this left-hand side of the hill, hit enter. And then it wants you to go to the right-hand side of the hill, so bring it over into this area over here. And once you're over there, hit enter twice. It jumps to 2.26 for the X max. And the Y max, which is the volume of this thing, is 194.07. Now, we have to be careful to answer the question. In the original problem here, it says, how much should you cut from the corners to maximize the volume of the box? So 2.25 inches is the right answer. And if you do that, if you took a little bit more than 2.25 inches out of each corner, your box would hold 194 and a little bit cubic inches. And that would be the maximum volume that this box would hold. Okay, that's it for this page 4 of the notes.